Okay, my wonderful students, let's get going. What we're going to do today is we're going to talk mostly about momentum. We're going to talk about some universal gravitation concepts, and I think actually Thursday I'll talk some more about gravitation as well. I've been working on some new material, and hopefully I'll be ready to work that out with you. But before we do that, I want to talk about your midterm exam results. Again, the grades page, you have three new lines. You have exam 1 Scantron, you have exam 1 clicking, and then you have exam 1 total. Now the first two lines add up to the third line, supposedly. And I think I've got almost all the bloopers squared away. So everybody should have a grade in there. Now one of the things that you can do with a Scantron exam is get a printout of what you bubbled in. Next to the answer key, and with that you can tell what answers you got incorrect and which ones you got correct. And that's kind of helpful. So, and I want to show you a typical blurb, or not a blurb sheet, a Scantron printout. And if you look at the top here in the upper right, it'll show you your grade, your points. I think it says total points. And we just go, whatever the Scantron gives for total points, that's what goes into the exam 1 Scantron line of your grades page. All right. Now, a couple things I want to point out to you. Let me make this a little bit bigger. You can look at each of your answers. Now, we had 45 items, and so there are 45 lines here, alternating color. And for instance, what you can look at is, okay, here's item 40. And for this particular student, this is an unknown, this is a student that messed up their PID. So it got printed out as a unknown student. But anyways, this is a real student, and they got exam question 40 incorrect. And you could see that because there's a letter X to signify that it's false. And what if you look at it carefully, when you get yours, if this was yours, you'd see that number 40 you answered B, but C was the correct, because the third column, actually the fourth column there, is the answer key. All right, the third column is your answer. The second column is, did you get it wrong or not? And the first column, of course, is the item number. So you can always see what you got wrong. Now, I can offer this to you as a PDF. I used to hand them out as printouts on paper, but I don't have a TA this semester, so I'm going to hand them out to you if you desire on PDF through the Web Courses messaging system. So to effect that, to get that to you, I've set up a homework, a one-question homework, 00, exam 1 Scantron PDF, and on that homework, you'll be asked, do you want your PDF? Yes or no? And you don't have to answer yes. You can write no. But if you answer yes, that'll mean you have a score of 1, because that's the correct answer. And if you don't want it, that means you got a score of 0. And that means I don't have to send it to you. But everybody that answers correctly, I'll know by their score, and then I'll send them their Scantron as a PDF. It's kind of a pain in the neck, but I can do it. It's fine. And just to reinforce, this is just a bookkeeping homework. So this is like the homework 0. So it doesn't go into your semester grade or anything. It's just me trying to find out who wants their PDF. Okay? Any questions about that? Yes. You can look at the actual test. I was going to mention it in a minute, but for right now, yeah, you can come to office hours and look at the actual test. And the ground rules are: you may look at the test, you may take notes, but you may not copy the exam questions verbatim into your notes. Okay. But in addition to that, in addition to just knowing that you got number 40 incorrect or number 26 incorrect, that's nice. But if you don't know what that question was about, what does that benefit you? So that's why I also publish a blurb sheet for each exam and each form, A, B, C, D, and E, or A, B, C, and D, depending on which form you have. Now the blurb sheet, this is a blurb sheet from, last fall. Okay, and it's also a PDF, and it's the same for everybody, so I'll be posting that on a certain page. Here's a close-up look at it. And you can, if you got number 26 wrong, you could say, all right, well, let me look at this blurb about it, and it'll have the answer key as well. So for last spring exam, this is exam 1. Look at those velocity graphs up there. Remember anything like that on the test? Yeah, hopefully you remember. Okay. So anyways, this is from last spring and exam 1, and you look up number 26. No such thing as horizontal gravity. Yeah, we had some questions. In fact, that was the answer to one of the questions for some of you. So anyways, if you get your exam 1 Scantron PDF of your results, and then the blurb sheet, you can look up the gist of every single question, especially the ones that you got incorrect. All right, now, so what that means is the Scantron PDF that you may ask for and the blurb sheet that you'll have access to in web courses, those will actually make a nice little kind of a mini study guide for the final. So because you'll be able to say, well, I got 26 and number 40 wrong, and they both have to do with horizontal gravity, so I better get that separation of equations of motion Galileo thing down pat before I get to the final. All right? And that'll help you sharpen up and crush the final, which I consider to be a fair thing. So in web courses, what it's going to look like is the blurb file page. I just set it up this morning, and there's nothing in there right now, but eventually later this week, maybe even this afternoon, I'll put the blurb sheets in there, and then when you get your Scantron PDF, you'll have the two things that you need for a little mini study guide for the final. So for instance, this afternoon or maybe later this week when I get the files up, I have to scan them into PDF and then post it here. But on this line here, yeah, that's where it'll be. So, and I'll let you know when I do that. It'll be obvious. So, and the exam blurb files page links to the home page. So when you log in, you'll see it on that little list of stuff down towards the bottom of the home page. Okay, questions about blurbs? Angelica. Good. Just practice the names. Okay. And to reinforce the question that you had, if this everybody can look at and can use if they have their exam PDF. If you actually want to look at not just the gist of each item, but the actual item itself, you may come to office hours. And so far, I've had one person to come to office hours, Wednesdays from 11 to 1. So if you want to come, if you want to start coming to office hours, we could do that. I'll have that stuff ready for you. Okay. And it's normal. We have students come. And you don't have to come right now. I mean, you can wait till later in the semester. There's no rush. By the way, this homework assignment is, it doesn't expire, so you have 47 attempts. So you can change your mind 46 times. Anyways, it doesn't expire, so you can do it anytime you feel like it. All right. I want to review a couple things using iClickers from the homework. And I want to go ahead and take notes on this. We're going to go through some of the homework items. And because just in the event that you got tripped up on one of them, I'm going to go through the skateboard interaction calculation. I think there were like 3 questions with Raymond and Gregory. And the last one was a calculation of how much momentum Gregory got, I think. And then the second one I want to review is the one with the medicine ball in space and the tractor beam and stuff. And you're going to have some clicking to do when we get through this. So let's do a little homework 6 review. So skateboarders, okay? The skateboarders, this is the key concept. When they interact, when physical systems interact, they're going to exchange equal but opposite momenta. So the delta P of one is the same size but the opposite direction of the other. Okay, so whatever Raymond gets, Gregory gets the same amount, but in the opposite direction. So with that calculation, you have to worry. Well, actually, I think let's see, Gregory was going to the right, so everything was positive for him. But you still had to handle your minus signs properly, and we're going to do that. So first bit of information is that Raymond has moved 1.05 meters in 0.2 seconds after the interaction. All right, so the patty cake that, Angelica and who else was that? Logan. Logan and Angelica. Yeah, when they did the patty cake experiment up here, they had contact, and then so this is 0.2 seconds after they break contact. So he's moved 1.05. Now, it doesn't say anything about Gregory's distance, but we're not asking about his distance. I mean, we could if we wanted to. Okay, so his average speed is actually just the quotient of 1.05 meters and 0.2 seconds. Speed is distance divided by time. Okay, so there's your calculation. So if you calculate that out, you get 5.25 meters. Now, Ray's momentum is leftward. Okay, so we could figure that out now. For figuring out delta P, you want to get your momenta calculated. Okay, so Raymond's actually his initial momentum is 0 because he starts at rest, right? Just like Angelica and Logan. So his delta P is equal to whatever this works out to. Now notice here, Letitia, I have the word leftward underlined. Now when I have that, I don't have to use a minus sign if I've got the word leftward in my sentence. But now if I want to calculate, I can definitely put my minus sign in there. So there's my minus sign in the velocity parenthesis in that third equation block. All right? And so that's kind of cinchy. There's your calculation. And in the third equation block here, that encodes the leftwardness with a minus sign. So you calculate. Anybody verify me on that? You got it?
No, I just have a question.
Do you verify? Just verification. You got it? Who's got a verification? Always bring your calculators and verify. It's good practice. Okay, Connor, question.
Yes, sir. So I thought you said when you underline leftward, you don't have to put a negative sign.
If there, repeat that.
Sure. I thought you said when you underline leftward, you do not have to put a negative sign.
Yeah, but now that this is an equation now. Okay, so this is the sentence, that's fine. But now down here, I don't really have a sentence. I just have a bunch of numbers and some units. All right. So in other words, I could put quotation marks up here and a period at the end, and then another quotation mark, or a set of quotation marks. So that's the sentence, and then this is the mathematical statement, and here's the mathematical equation. And I could write this one here without the minus sign, but then I'd have to say comma left. Okay. So there's Raymond's delta P, negative 393.75. And in the problem, I think it rounds to the nearest tenth. So 393.8 negative. And therefore, Gregory catches the exact opposite. And that's the answer for that equation, for that problem. For this version of it, there's like, a bunch of different random versions, not different mass. I think different speeds and different force, different, at least one, I can't remember what's different. Actually, seconds, the time, delta t is different. Okay. Yeah, so different delta t means he's a little bit faster, a little bit slower, therefore a little bit more momentum or a little bit less momentum. But you do it, this is your basic way for doing it. Okay, now let me pause for questions. Go ahead, Connor.
Just clarifying, so left and right and up and down, so down will be a negative sign as well?
Yeah, unless you're one of these guys that likes to do the opposite of everybody else, anti-everything. But yeah, most of the time it's down is negative, left is negative. But you can do it either way, as long as you're consistent. And then as long as you can translate it into an English sentence, like 1D, because there's no minus signs or plus signs there, just a word. So if you can do that, then you're good. All right. Question, Angelica. So Angelica just said, Dr. B, I multiplied 75 by 5.25, then by 1.05, then divided by the time. Yeah, that's basically what I did. I just did it in different order. I did the distance divided by time first, but you did mass times distance divided by time, so that's cool. Yeah. So, and keep that in mind, like when you're in discussions and somebody's chipping in some pointers and stuff and helping you on the homework, it may be different than the way I explain it, but still be righteous. So keep that in mind. There's more than one way to skin a cat, or more than one way to describe skinning a cat, I guess. Now, I want to ask you a question. Now, this does not have to do with physics, but has to do with teaching. Raise your hand if you're an ed major or hoping to become an ed major of some kind, elementary ed or secondary. Okay, good. Now, I just want to let you know, you may have noticed whenever I go and whenever I say, let me pause for questions, and I just look at you and wait. I don't say anything. I wait for 15 seconds. I can see the timer on my screen here. I look at it, and okay, 15 seconds. And that's called the 15-second rule. And usually, and this was something that one of my old profs in grad school, one of the best profs at the time, he's retired now, but he said, always use, because for grad students, they always teach you, they expect you to be a lab TA and a grader and stuff. And I was teaching all the way through I was doing this all the way through grad school. But anyways, he always told us, Mac Rugheimer, use the 15-second rule. And usually if you wait 15 seconds, somebody's going to ask you, like Connor, I waited 15 seconds and you came in at 14. So it's right. So and they usually, but if nobody comes in, then you keep going. All right, so let me show you what 15 seconds is. If you have a question about the 15-second rule, let me pause for questions starting now. "15 seconds. Seems like an eternity, but it works. So in case you're wondering why do I say that and I'm just staring at you guys, that's why, because I want you to come up with a question. If you got one. If you don't, you don't. All right, let's keep going. So, and you guys that are ed majors, boy, I love you guys because it's a good, teaching is a lot of fun. That's why I like working here at UCF. I love most of you guys here at UCF. Most of the time, work your off. I love working with UCF students. Compared to some of the schools that I've been to, like Ivy League schools, that sometimes not so hard working. But anyway, so that's the skateboarders problem. Let's do the next one, the medicine ball in space. So this one, if you have a stopping time problem, immediately write down F delta T equals delta P, because most likely it's going to be the easiest method to calculate a stopping time. All right. So there it is up there. And so what we want, on the medicine ball problem, we need a force. We want the delta T, and we'll calculate that if we can get a force and a delta P. All right, so we got to have some specs here. The first thing is that the tractor beam is south. In this case, Connor, to the left is south. Okay, so that's going to be negatory. 1.6 newtons in this example. And I think this is one of the factors that changes each time you do this, the medicine ball problem. And then the initial speed of the medicine ball is the opposite direction, to the north. So that force, that tractor beam, is going to pull it gently to a stop. All right? And then it's going to start sucking, and it's going to stop and start coming towards your spaceship. But we're not going past the stopping point. So its initial speed is 6 meters per second north, and that's off to the right, as the red arrow shows. All right. Now, the other easy point, initial speed V1 is 6 meters per second north. V2, stopping velocity 0. That's the easy one. All right. So if it's a stopping time problem, V2 is always going to be 0. All right. So delta V you could figure out. Final minus initial. V2 minus V1, so 0.0 meters per second minus 6 meters per second. And so your delta V is negative 6 meters per second. So that means you can figure out delta P. In other words, the right-hand side of the impulse equation, because that's just the mass of the medicine ball times times delta P times delta V. All right, so, and the mass of the medicine ball in this example, 1.34 kilograms. I forgot to put that up at the top, but that's what it is, 1.34 kilograms. That's right here in 2E. Okay, here's the mass, and here's my delta V, negative 6 meters per second. So my exchange with the spaceship by way of the tractor beam is the medicine ball absorbs or acquires negative 8.04 kilogram meters per second. Anybody verify that, 8.04? Go ahead and double check me on that. So, because sometimes I'm typing so fast, I bloop it up, but good, all right. So now the spaceship is going to acquire a positive 804 in this interaction, but a spaceship is not going to, do anything because it's a lot bigger than the medicine ball. Anyways, so that's what we got. All right, so now we could put that into the impulse equation because now look up here at the very top. We have delta P, that's negative 8.04. Oh, and by the way, jot down everything in this because your first clicker question is going to be asking about this medicine ball but with a different tractor beam. Okay, we're not using this high quality Acme tractor beam like you have on the homework. We're using brand X. All right, slightly smaller one. But anyways, delta P, we've got that. And yeah, we have the force of the tractor beam, F. So now all we got to do is plug this in and just start to cook. All right, so here we go. There it is, negative, and it's a leftward. Connor, here's my minus sign, good. And delta T. So we're doing good there. Okay, Casey? And then I got my negative 8.04 kilogram meters per second on the other side. Okay. And now I just got to clear the left side, get delta T by itself. And of course, that's fairly cinchy. Just, divide both sides by negative 1.6 newtons. Now remember, a newton is the same as kilogram meter per second squared. And so these things all cancel out except for 1 unit of seconds. And verify me on that. Is it good? Okay, good. All right, we got verification. And on this one, the round off was to the nearest hundredth of a second. So this one would go up to 5.03 seconds. All right? Now, I'm going to let me start up a session here. Go ahead and hold on a second. Come on, baby. There we go. Okay, now this one's going to be numeric. So go ahead and we're on frequency DD. How's your clicker back? What are you doing way back there? Don't look around. Yeah. You can sit down here in the front if you want. You sit wherever you want. Anyways, good to see you. Is your clicker clicking? Did you get a Go Nitro? Yeah. Sweet. All right, here's your question. Same medicine ball. Tractor beam is brand X, a little bit smaller, 1.1 Newton. Question. That's the mass of that was one of the random variables in the that's the mass of the medicine ball. So use that again. Use 1.34 for the mass, negative 6 for delta V, and get delta P, and then use this for the new tractor beam force. Okay? Diamond? Yeah, good. Okay. Yes, question? What did I say, what? Oh, you mean the numbers that you're supposed to write down? 1.34 kilograms for the mass. And the initial velocity, 6 meters per second north. So, and then 0 for the final velocity. Good? Yeah? Okay. This is, but by the time we get to exam 2, this is going to seem like child's play. But right now, it's probably a little bit tricky for you. That's why we're doing a little extra reinforcement. Diamond. Yeah, so the only thing that's different, it's the same medicine ball, but now we're using this weaker tractor beam. So the F is different. 1.1 instead of 1.6 on the example that I worked out. All right. Who in here is secondary ed major? Anybody? Bueller? Okay. You're secondary ed. Anybody else? Who's early childhood? Okay, good. So everybody else is elementary. Yeah, okay. Good. You know the smartest student I ever had here at UCF? Oh my goodness. She was an early childhood ed major. And I had her for this class and then astronomy the next semester, and she crushed it like a bug. But I said, what? Simone, why don't you become a physics major? I mean, you obviously like this stuff and you're good at it. And she said, oh no, Dr. B, I'm just going to. And I'm sure she's a fine elementary ed teacher. All right, 77 answers, 30 seconds. Who's still working? Okay. What's that? You what? Can you help me, please? No. But your neighbors can help you. No, they don't know either. Uh-oh. I've never seen a student walk across the room and do that. That's excellent. The boy in the red hat. Yeah, everything goes back to the impulse formula. So the plug-in here is 1.1 instead of 1.6. So we should be, let me see what you guys are voting for. Make sure you round off correctly. And also, all right, I can see some answers here. And I see a lot of correct answers. But you know what else? I see some negatives. Delta T is supposed to be a positive number of seconds. Because remember, it's negative divided by negative when you actually calculate it. But you guys are doing good. Okay, 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Man in the red hat. Thank you for doing that. To the rescue. Anybody come up with this? Raise your hand if you came up with 7.31. Sweet. All right, so there's your answer. And good. I may put another one of these babies on the homework due Thursday, which I'll try to set up this afternoon. And it won't be a big, huge one, but I might put one of these on there. Yeah, Connor.
Kept getting a negative 7.31.
Because you...
It couldn't be negative because of time.
Yeah, and I saw a bunch of people answering negative 7.31. So, yeah, on this one, in the impulse formula, F is negative 1.1 newtons. All right? Delta P is still diamond negative 8.04. That part's the same as the other, the previous example. So to get delta T by itself, you still have negative over negative. All right, so it should be a positive. So now we're doing it in class. Try to remember it on the next exam. Okay? Just one of the things to worry about. And yeah, I see a few of you guys answer, you rounded off a little bit improperly. Try to do that carefully. 2 people typed in 7.32. Wrong round off. Okay, we'll do some more clicking in a few minutes. Let's get back to universal gravitation. We did start talking about this, and I wanted to, we'll just reinforce, because we're going to apply uniform circular motion concepts, like centripetal force and stuff like that, to the idea of universal gravitation that Newton developed. Now, the 2 physical factors were the mass of each object, so like the Earth and the Moon, the mass of the Earth and the mass of the Moon, which nobody knew the mass of the Earth or the mass of the Moon at that time. Now, we do now. We know how many kilograms we've got for each, but at that time they didn't. But you could still do everything proportionally and stuff, so they worked it out. The other factor was the physical distance. Now they were able to figure out the distance to the moon fairly accurately. Right now we've got guys at NASA. They have a telescope, a big astronomical telescope down in Texas, up on this mountain in Texas, and all they do is they bounce laser beams off the moon. And the Apollo astronauts left some reflectors up on the surface of the moon. So when they aim a laser at those reflectors, they'll get a bounce back. And when they do that, they can actually, they time it. How long does it take to get back? They know the time it starts out from Texas. How long does it take to go to the moon and back to Texas? And when they do that, they can figure out the distance. So they're continually doing that. Well, not continually, but they're doing it a lot. We know the distance to the moon to within a few centimeters at any given time. I mean, in Sir Isaac Newton's day, they didn't have nearly that much precision, but we do now using those lasers. So lunar laser range finding. It's a big topic in theory of relativity. So the idea that Sir Isaac Newton said was, if you have more mass, you're going to have more force, okay, for gravitation. So those 2 babies, the mass of the Earth and the mass of the moon, if you have some kind of equation, at least you know that they're going to be in the numerator. Because if they're in the denominator, the more mass you have, that would make the force smaller. But mass, bigger. But now distance, the more distance you have, the weaker. And as I mentioned last time, this is the actual formula. A multiplication constant, G, capital G, that's called Newton's constant, or the gravitational constant. And then mass 1 times mass 2. That's in the numerator. That's like mass 1 is like the mass of the Earth. Mass 2 is like the mass of the moon. Or it could be, the mass of a comet and the mass of the sun. They're gravitationally interacting. Or it could be, the mass of a black hole and the mass of a nearby star, and they're orbiting each other. We see binary stars out the wazoo. Most of the stars that we see in the sky are in pairs, binary star systems. It's kind of cool. Then down in the denominator is the distance center to center. And it's not just the distance, it's the square of the distance. Okay? And, it was a conjecture of Sir Isaac Newton that would be the distance dependence. And go ahead and make a note to yourself, it is highly significant that the exponent there is 2. In other words, it's inverse r squared. It's not inverse r to the third. It's not inverse r to the first power. It's not inverse r to the 3/2 power. Something to the 1/2 power is a square root. It's not r to the 9th power. It's not r to the 2.07 power. And we've measured this very, very carefully. It is r to the 2.00000. We can't get to the end of the zeros. We've never found anything other than zeros. It looks like it's exactly 2. And what that means is a couple things. First of all, the gravitational force is infinite range. That means that every object in the universe is interacting gravitationally with your left earlobe, with every atom in your left earlobe. And every atom in your right earlobe is interacting with every atom in your left earlobe. It's not very strong, but yeah, theoretically they're interacting. You don't notice it, but the interaction between you and the Earth is not the only gravitational interaction that you experience. And here's a significant gravitational interaction that we can measure. Tides. The tides in the oceans of the Earth are gravitational because of the gravitational interaction with the moon. And we can actually measure tides, much smaller, but measurable, because of the position of the sun. The sun does to the oceans of the Earth in a small way what the moon does to the oceans of the Earth in a lot bigger way. So when the sun and the moon are lined up, you get really deep low tides and you get really high tides. If the sun is on one side of the Earth and the moon and it's a full moon, and the moon is, like right now we've got a full moon. So the low tides are going to be a little bit lower than normal because they're both in the right position to achieve a big high tide and a deep low tide. So that's why a hurricane that comes through right about now, you're going to get if it comes through at high tide, if it makes landfall at high tide, you've got a storm surge on top of a high tide. So you got a big trouble. And occasionally hurricanes do that. So the inverse r squared first. Go ahead and write down that phrase. It's important. It's also in your textbook. Inverse r squared. Not all forces are like that. The nuclear forces that hold the nucleus of the atom, no. But it turns out that the electromagnetic interaction, static cling, between electrons and protons, for instance, yeah, that's 1 over r squared as well. Slightly different form, and we'll get to talking about that in a few weeks. But yeah, 1 over r squared, infinite range. And the other thing is, it means the mass of the graviton, which is how the gravitational fields are exchanged, the mass of the graviton is 0. Now, the graviton is to the gravitational interaction what the photon is, a particle of light, is to the electromagnetic interaction. So the oscillations in the electromagnetic field that we perceive as light can be quantized into little bindles of energy called photons. We can model everything as photon interactions electromagnetically. And those are infinite range. The speed of light They travel at the speed of light and only at the speed of light. And graviton's the same. So it's been very, very well verified. And even in even in Albert Einstein's theory of relativity, with black holes and neutron stars and things like that, pulsars, it hasn't replaced this. This is still in effect. It's just a different way of looking at this force. So this is highly kosher, highly righteous, and well verified scientifically. Now, let's talk about satellites. All right. Now, here's where we're going to put together centripetal force and universal gravitation. All right. And so, in other words, we're going to synthesize these two things. So, let's think of a simple system, the Earth and a satellite orbiting the Earth. So, the mass of the Earth is capital M, and the mass of the orbiting satellite is M subscript S. So, I have a little s down there. All right? Now, the distance is something that, NASA says, well, I want this satellite at a certain altitude over the Earth, a certain distance from the center of the Earth, therefore. And so they set that, and, they have to have the right size rockets, so they got to get all this stuff squared away, but they can do that. Now, if it's a circular orbit, not elliptical, and we have plenty of elliptical orbit satellites, but if it's circular, we got plenty of those, you can use the centripetal force formula fairly easily. All right, so let's put those two together. All right, so on the right here is mv squared over r, and m over here on the right is the mass of the satellite. That's the thing that's on a circular path. All right, circular orbit, circular path. So it has to have some force towards the center. That's gravitational force. So that's why the left-hand side here, here's the F of F equals ma. It's gravitational force. So G, capital M, times M subscript S over R squared. All right. F equals ma. Ma is on the right. The mass of the satellite times the centripetal acceleration. Good. And then on the left, the force, Gm times ms over r squared. By the way, I forgot to mention about the gravitational constant G, capital G. And I go into it in the textbook, and you should be reading in chapter 3 and chapter 4 this week. We'll probably finish chapter 4 next week and just keep plowing forward. Anyways, capital G, Newton's constant, the gravitational constant, it turns out to be important for Newton's law of universal gravitation. In this formula, Gm/ms over r squared, capital G is like a multiplying factor, a conversion factor. In other words, it converts, the numerator is kilograms squared and the denominator is meters squared. Now that's not a Newton. I mean, the left-hand side is supposed to be Newtons, kilogram meter per second squared. But the measurements are two masses, so kilograms squared in the numerator, and square of a distance, their mutual distance, so that's meters squared. That's not a Newton. So Newton said, well, let's put a constant in there to be the conversion factor. And here's what I mean by a conversion factor. If you think of, for instance, conversion, like you're in 7th grade and you're learning the Celsius temperature scale, or 6th grade, or whenever you learned it, 10th grade, and there's I can't remember how it goes. You multiply by 5/9 and subtract 32, or you multiply by 9 over 5 and add 32, to get from Celsius over to Fahrenheit. Well, that factor of 9/5, 5/9 is a conversion factor for Celsius to Fahrenheit, and from Fahrenheit to Celsius. All right, so let's see, 5/9 would be the conversion factor from Fahrenheit to Celsius. 9/5 would convert Celsius to Fahrenheit. And then you got plus or minus 32 and a bunch of multiplication. But anyways, those are that is a factor, 5 over 9, 9 over 5. Those are conversion factors, Celsius to Fahrenheit, Fahrenheit to Celsius. Okay, so that's good. Now that's what this is. Capital G is a conversion factor from kilograms squared per meter squared to a Newton of force, kilogram meter per second squared. So it has weird units, and you can look it up, in the textbook. Question? Can I repeat? No. I was talking for about 5 minutes about it. Oh, okay. Capital G converts kilograms squared per meter squared, which are the measurements in the numerator divided by the denominator, right? It converts that into newtons, kilogram meter per second squared. All right, and that's just like, it's similar to converting Celsius to Fahrenheit. You know what another one? Here's another conversion factor you might know. From English pounds to kilograms. Anybody know the conversion factor there? It's pretty cinchy. What do you do to get from kilograms to pounds? Multiply by what? 2.2. Miles per hour and meters per second. That's about 2.24, right around there. So, Connor.
So what's the actual number?
G?
Yeah.
In the metric system, it's 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Connor? You do not have to memorize that. I surprised myself that I actually know it, but usually I just have to look it up. But I've been thinking about what G is, because it turns out that G is also important for defining the distance scales, the size of a black hole. In other words, so many kilograms of mass means your event horizon, the point of no return around a black hole, is that it sets the distance. The mass and Newton's constant and the speed of light set the distance of that event horizon, the point of no return. So it's actually, capital G is also, in addition to being a conversion factor, it's also like this fundamental unit of the universe that is indispensable in the theory of relativity.
When you do the computation, what do you do with G? Does it go away?
No, it's just you compute with it, but you're not going to compute with this. Okay? Don't worry about that. All right? But we're not done talking about it. Let's keep talking. Let's keep going. So here's your little aid to memory. Gravitation on the left, centripetal force concepts on the right-hand side of that equation block. All right. Now let me clear this out. Now, one of the things that you might notice, anybody notice anything kind of handy or convenient about this equation? See anything? Don't look at me. Look at that. Look at the equation. What do you see? Hold on. What do you see? That's right. You can cancel out MS. I prefer to burn them out. So go ahead and cancel those babies. All right, so that makes it a little bit simpler. And now we're getting down to brass tacks. And so, Connor, this is one of the reasons that we're not going to calculate with this, but we are going to think with it. All right? And because another thing that I can, any other simplifications that I can make? You see anything? What's that? R, yeah, we got R. So let's cross multiply the R over to the left, and that cancels 1 from the bottom. All right, so that's about as simple as she goes. G times the mass of the earth divided by R. And that's equal to V squared. And notice, in this, the mass of the satellite, what is your name again? Adriana. As Adriana mentioned, the mass of the satellite cancels. So this expression here holds for any size satellite. I mean, within reason. It can't be as big as the Earth. I mean, any man-made satellite is going to hold to this. All right, so what it means is if I set R, I can figure out V squared. If I set V, I can figure out my altitude and my radial distance R. All right, and there's reasons to do that. So let's get this over here. So there's my GM over R and V squared. So let's say, for instance, you know the radius R that you want, and so you can figure out the required V, and then design your rockets, because a rocket is going to have enough rocket fuel to get you up to the right speed. And you don't want to have any extra. All right? You don't want to lug any fuel that you're not going to use to the launch pad and up from the launch pad. You want to have just enough so that so you reach orbital velocity V just when the last ounce of rocket fuel burns off, plus or minus. So we're not talking plus or minus a ton. We're talking plus or minus some ounces, hopefully. Anyway, so that's what they got to do. Now, when would you want to do that? Well, setting the radius means, for instance, I want to have a low Earth orbit, close enough to keep an eye on the Russians. And back when I was your age and before that, that's what us Americans, we had buku satellites looking down on the Russians 24 hours a day, as many as we could get up there. The Hubble Space Telescope that everybody admires. They don't mention it, but the military and the CIA have got probably about 70 of those things up in space looking down at the Russians. So they see everything. And the Russians have got the same similar gear looking down at us. And a few other countries like China and stuff. They don't have as much, but the Russians definitely. I mean, it's the space race. Space race. So you want a satellite to spy on the Russians? Yeah, okay. Just tell me how low you want it. I'll build the rocket. I'll get it up to the right orbit at the right speed. Bing. Circular orbit. Just keep cooking. And NASA can do that. The Air Force, they can do that. Now, what if you need a certain orbital speed? All right, you can figure out the required altitude and radius of the orbit. So, altitude is from the surface of the Earth, but the surface of the Earth is about 6,371 kilometers from the center. That's something I memorized. The radius of the Earth, I'd have that memorized now, 6,371 kilometers. So the distance out to your object is from the center of the Earth out to your satellite. And subtract 6,371, and that'll be the distance from the surface up to the satellite, the altitude. So when would you want something like that? Well, how about a satellite that's fast enough to orbit the Earth once per day? So the thing about that is, if it orbits the Earth once per day, that's nice. But the Earth is spinning once per day as well. So if you have a satellite that is circling the equator once per day, and then the Earth is spinning, from the North Pole to the South Pole on that axis, and halfway between is the equator. If it's spinning once per day, your satellite is going to seem to be stationary. Somewhere above the equator, wherever you set it. You know, because it's going to be moving on its circle, and the equator is going to be moving on its circle once every 24 hours. So they never catch up. You know, it never gets behind. The Earth doesn't get behind. The satellite doesn't get behind. They stay right on top of each other, and that is what we call a geosynchronous satellite. And if it's orbiting the equator, we would call it geostationary. Okay, you can have a geosynchronous satellite that, you know, orbits the North Pole, the South Pole, or North Pole, South Pole once per day. And there's uses for that. Or you can have one that's tilted at 45. You know, it goes to 45 degree north latitude, 45 degree south latitude, 45 degree north latitude, and blah-de-blah all through the day, or every day, once a day. And I suppose there's uses for that. But, you know, geostationary, you know, everybody's, you know, when Hurricane, what was that? Florence. Whew, boy, they dodged a bullet up there in North Carolina, boy. Actually, still a lot of people got killed, but can you imagine if that had been Force 4 or Category 4 or Category 5? Oh my goodness, that would have been horrible. Anyways, everybody's looking at the satellite images. And a lot of those satellites are geostationary. You know, and they're stationed over the Atlantic. That's the spot on the Earth where the satellite is stationed. If you have direct TV or any kind of dish TV, you're looking, you got to aim those dishes at a certain satellite, you know, certain tilt angle, certain, you know, direction from your house. And the guy from the direct TV company comes out and does it, I guess. And you get the signal from that satellite. It's just, you don't have to adjust it after you get the signal, you're good. Set it and forget it. Geostationary. All right, inverse R squared force. I've mentioned this already. I want to mention a couple other things about this. What Sir Isaac Newton proved using calculus, and actually without using calculus, supposedly he only used trig to prove, he invented calculus, but supposedly he only used trig to prove the laws of motion of planets around the sun. Now, a few years prior, maybe 50 years prior to Newton, there was a European named Johannes Kepler. And he was an astronomer, Johannes Kepler. And he had kept records, and he studied other people's records of planetary positions. So Mercury, Venus, the Moon, Mars, Jupiter, and Saturn. Those are the planets that he could study, because he didn't have a telescope. So he didn't know anything about the moons of Jupiter or the moons of Saturn, but he did know about Saturn, Jupiter, and on in from there. And he was able to find a pattern. And one of the patterns was that the planets move on elliptical orbits. They don't necessarily follow circular orbits. All right. Now, the biggest two ellipses that he was able to work out were Mercury's orbit and Mars's orbit. Mars is the one that got him to figure this out, that every planet is on an elliptical orbit. Now, Earth's orbit is elliptical, but it's really, really close to a perfect circle. If I were to draw out Mars's elliptical orbit and a perfect circle, you'd have a hard time comparing those two. And Earth and a perfect circle, even harder. But Kepler figured it out. He also figured out this one, that in equal times, a planet, each of those little wedges, the blue and the white and the blue and the white, each of those wedges have the same surface area, different shape, different shape slice of pie. But if you count up the square centimeters, or actually the square kilometers, because it's a planet, it all, they're equal times and equal pie slices. So that's his second law. And his third law says that that there's a relationship between the size of an orbit and the orbital period. And Sir Isaac Newton, and now he discovered those numerically by studying big, huge, I don't know, he must have had like really good eyeglasses or something. He studied it because he was just looking at the numbers. And, a lot of scratch paper, a lot of pencil, went through a lot of erasers. But he worked it out. I don't know how a person could do that, but he did. And so this is, so here's the three laws that Kepler figured out from the numbers. Sir Isaac Newton proved that if the universal gravitation is gm1 m2 over r squared, this has to be true. So he basically figured out the theory underneath Kepler's three laws of planetary motion. So the third law is one that we still use a lot. We actually use it to measure the mass of a black hole in a binary star system. Average orbital distance to the third power is proportional to the orbital period to the second power. Here's the fancy form of it down here. Orbital period squared equals a big constant in square brackets, 4 pi squared over g m1 plus m2 over times the average orbital distance a to the third power. And my wonderful students, this works in the solar system. It works in every binary star system that we see, and this is how we measure the mass of stars. And Sir Isaac Newton said, F equals ma is why this is true. All right? Now, Edmund Halley of Halley's Comet, he was friends with Sir Isaac Newton, and he knew all about these orbital laws and why universal gravitation put a lock on them. And so he surmised that comets also follow elliptical orbits. So Kepler said, dude, Mars is on an elliptical orbit. Dude, Mars is Mercury, Venus, Earth, Saturn, Jupiter. They're all elliptical to some degree, especially Mars, especially Mercury. But he could measure out, the elliptical orbit of Saturn and Jupiter. And all these other laws. And Sir Isaac Newton said, yeah, I got a lock on that. F equals ma, gm1 m2 over r squared. Ding. I got it. Kepler, your laws are righteous. And so Halley said, all right, fine, planets, nice. How about comets? So Halley said, yeah, let's think about comets as going in elliptical orbits. And if that's true, they'll return periodically, just like planets. I mean, the moon goes around, on its orbit around the Earth once every 29 days or whatever it is. And, planets, Mars, I can't remember, Mars I think is like 2 years or something like that, 2.2 years. And so Halley was interested in comets, and he'd actually studied a lot of them from the historical record. So here's what he figured. He said, look, we had a comet in 1531. And that's the days of Cortez landing in Mexico. 1607, that's the days of Shakespeare. 1682 was in Halley's and Newton's lifetime. That was contemporaneous with them. And he said, I think that those three comets are the same comet. And that if they are the same comet, as I predict, they're going to come back, or that comet is going to come back again in 1758. Halley's famous prediction. And by God, it did come back right at Christmas time, right at the end of the year. And that, my wonderful students, is like the crowning verification of Sir Isaac Newton's law of universal gravitation. They predicted it. You know, he explained Kepler's laws, but he predicted, and Halley predicted, the return of this comet right on the money, right on time for Christmas. Of course, Sir Isaac Newton and Edmund Halley were both dead by that time, but they'd passed on. But it doesn't matter. Their prediction, right on the money, my friend. And that is what we call cha-ching, money in the B-A-N-K. And so that gives confidence, that kind of experimental verification gives confidence to every scientist that studies the law of universal gravitation. All right. I want you to finish reading chapter 3 and start reading chapter 4. I'm going to dismiss you a few minutes early today. We're going to talk about collisions on Thursday. So be ready. You're dismissed.